So my name is Raphael Hauser. I'm a faculty member at the Oxford Mathematical Institute, and I will give this masterclass on discrete optimization. My colleague Coralia Cartes has already given a course or a few hours on continuous optimization. And so there are really kind of two different aspects to optimization. Often you have continuous structure and you have a discrete combinatorial structure or variables that are forced to be integers. And this is very much what I'm going to talk about today, integer programming or integer optimization models. And so to motivate what I'm going to do, I would say can't say resuscitating, but this is sort of how I see it, an old technique. So what I'm going to talk about is an old technique for solving large-scale integer optimization problems with a particular structure. And that structure is a structure that we also now see and very much exploit in big data optimization problems, in particular in lasso problems and feature selection problems in machine learning and in dimensionality reduction problems in data science. So in the case of continuous optimization, the exploitation of this structure, and the structure is a partial decomposition of the problem, and so kind of a divide and conquer, if you will, methodology has created huge activity, research activity in recent years, and huge excitement. However, historically, the first such problems where that kind of structure was exploited were integer programming problems, because I think they hit much earlier on, they hit real boundaries to the size of problems they could solve. So even a few hundred variables is a big problem, right, when you have integrality constraints. And so there are essentially two approaches, right, that were developed to exploit this partial decomposition. One is called Lagrangian duality, which I'm not going to talk about today. And the other one is delayed column generation. And this is known, depending on the variant that you look at, under different names. There's also the dual approach to this called Bender's decomposition. It's also known as Dantzig-Wolff decomposition or Dantzig-Wolff reformulation. In order to get to the point where I can explain what this is about, I will have to also give you an introduction to integer programming. That's a sort of a whirlwind introduction, but at the same time, I'm going to do this with some very easy examples, which hopefully give you the flavor of what's going on. And so that's another benefit that you get from this. If you don't know about integer programming, then you will, by the end of these lectures, hopefully be interested in learning about it more. Now, like I said, these are somewhat classical techniques, and therefore the sources that I used and that I also recommend for further reading are not that new. But still, I think this is a very topical theme because I've recently started working with Oktay Gunlug from IBM and with my student Rika Kovacs, with whom we started looking at dimensionality reduction in for data science problems that involve categorical variables. And then naturally you end up with this type of structure and these type of problems. So what is integer programming? Integer programming is, or linear integer programming, are problems of this form whereby you have a bunch of decision variables, say n decision variables, which are collected in a vector x, and you want to maximize or minimize the linear function of these decision variables subject to linear constraints and then also integrality constraints. So each xi must be an integer, and then I require I to be, or x to be a component-wise non-negative vector, and then I also have vector inequalities. So A is a matrix, an m by n matrix multiplied by x gives you a vector size m, is component-wise smaller or equal to some other vector b. So what renders this problem hard is this integrality constraint. So if you don't remove the integrality constraints, you're looking at what's called a linear programming model, and these are the oldest types of optimization problems that were studied algorithmically, and indeed gave the name to the activity of computer programming, as in writing code, because linear programming, the solution of linear optimization problems was called linear programming before there were computers to solve such problems. So there are special cases. Like I said, if you remove the integrality constraints, it's called a linear programming problem. If all your variables are constrained to be Boolean variables, that is 0 and 1s, then this is called a binary integer programming problem. And then there are also mixed linear integer programming problems whereby maybe I have a vector of decision variables which I decompose into two blocks, x and y, and I only have integrality constraints on one block but not on the other. So, give you an example. Why is this interesting? Why should we look at such problems? So I can recycle this example later on when I explain the column generation principle. So here we have what's called the facility location problem. So you're maybe Amazon and you need to decide where you build distribution centers, and then from there you service certain clients, or maybe these are warehouses for say Sainsbury's or another big company, and they need to decide where to build their distribution centers, and then from which of these distribution centers they service various clients. So we have a set of potential locations for these distribution centers that have been identified. Let's call that set N. And then we have a set of clients, which is usually a much larger set than the number of distribution centers. And there's a revenue Cij per unit of the total proportion, if you will, of the total service required by client I when it's serviced from location J. This revenue may depend on which location you pick, because maybe there's a longer road, costs are higher, and so on. And there's also a fixed cost for building and or running each of these locations. And so you will not build all these locations. You want to know which locations should you build, right? And you want to satisfy all the demands. And so, this is kind of, if you think it's a factory or production centers or warehouses from where you go to different clients, right? And so which of these locations should you build? So how do we model this as a mathematical programming or optimization model? We need to introduce some decision variables. So for each pair of client and a location, we introduce a variable xij, which is the proportion of total service required by client I serviced from location J. Then we have binary decision variables yj, which take the value 1 if the location J, the facility at location J is built, and 0 otherwise. So these are kind of flag variables. And then our objective is to maximize the total revenue minus the cost. So the total revenue is this sum minus the total cost, and some of the yj's are equal to 0, but we have to be cognizant that if yj is 0, meaning that we're not building a facility in location J, then we cannot service any proportion of service of the demand of any client from that location. So therefore, we're not completely free in choosing our decision variables x and y independently of one another, the dependencies, right? And we need to model these dependencies. And so that happens through constraints. So on the one hand, we have these constraints on the demands that simply say that if you look at the proportion of demand for client I service from location J and you sum that over all the locations, then that must add up to 100% of that client's demand. So you're satisfying all the demand of this client. In total, you may break it up over different locations, but you want to service all the demand of this client for each client. So for every client, I have one of these constraints. Then there's this requirement here that says that my xij's must be proportions of service of the demand serviced for client I. So therefore, these are numbers between 0 and 1. And then, most importantly, we have these kind of constraints here, which take a flavor of what's called a big M constraint in integer programming. Now, in this case, is a very simple type of constraint. This constraint simply knowing that yj is a Boolean variable. If there is at least one client client I for whom we service at least a strictly positive, whatever so small proportion of their demand from location J, then that has to force yj to be equal to 1. In other words, that facility at location J has to be built, right, or opened. Otherwise, we can't service that. On the other hand, if all the xij's are equal to 0, then it could not be optimal to still build this location and just let it idle around. Okay, so we put all the elements together and we end up with a mixed integer programming model whereby we want to maximize our profit minus or revenue minus the cost, subject to the constraints that we introduced. And of course, x here are continuous variables constrained between 0 and 1, but I don't necessarily have to put this upper bound because it's implied by this constraint as well, so I can get rid of it. And y are binary variables, so b is my notation for the set 0, 1. It's just binary instead of binary variables. Okay, there are a huge number of other applications for integer programming problems, mainly in logistics, but also in supply chain management, in scheduling, in routing traffic through networks, in public key crypto systems, and so on and so forth. The application, an emerging application that becomes increasingly more important in data science is feature selection in machine learning and dimensionality reduction. I'm not going to talk about these applications today, but I'm happy to give a talk about this at another date. Now, we want to talk about algorithms for solving integer programming problems, so large-scale integer programming problems that have special structure. And before we can do that, we need to talk about general approaches to solving IPs. Integer programming is known to be an NP-complete problem, and one of the sort of powerful general techniques that have been developed for solving such problems is branch and bound. And so we want to look at LP-based branch and bound, and this will become clearer as we go through the next few slides. But to do so, I need to explain, and for most of you this is a repetition of something that you know, what the simplex algorithm for linear programming does, linear programming being the special case where you don't have any integrality constraints. And I'll just go through a simple example that highlights the main principle behind this simplex algorithm. I'm using the simplex algorithm specifically because the technique that we'll discuss later on ties in very tightly into this simplex methodology. So there are many other algorithms for solving LPs, but they don't lend themselves as well to that exploitation of the specific structure that we'll look at later on. So here I have an example of a LP problem. I want to maximize a linear function of 3 variables subject to linear constraints. In this case, I've got 3 constraints, but this could be 7 constraints. It doesn't matter. So it's a coincidence that the number of constraints is the same as the number of variables. And my variables are non-negative. And so the simplex algorithm, the easiest way to understand it, if you've never seen it before, or maybe you've seen it before but you didn't understand it this way, and then it's interesting in its own right, is to see the simplex algorithm as just a sequence of reformulations of the same problem. So you kind of say, oh, no, I want to represent the data in a different way. And, we will see that when you find the right reformulation, you can sort of just read off what an optimal solution is, and it just reveals itself to you. That's the magic. But it's really quite easy to understand. So the first thing that I do is I would like to turn all these inequalities. Remember on the previous slide it said 2x1 plus 3x2 plus x3 smaller or equal to 5. I would like to deal with equalities rather than inequalities, simply because we know about linear system solving and so on. So what do? I just add what's called a slack variable. So if this left-hand side is smaller than 5, I can always add something non-negative to make this equal to 5, right? Likewise for the second inequality, if these terms are smaller than 11, for my choice of variables x1, x2, x3, then I can add some other quantity x5, which is non-negative, so as to make this equal to 11. And likewise for the third constraints. So therefore, I also have inequality or non-negativity constraints on these slack variables. So far, this is just the first reformulation. Of course, it's exactly the same problem. If you will, I reformulated it in a higher dimensional space. Instead of deciding on x1, x2, x3, I also have to somehow settle my mind about how I choose my x4, 5, and 6. But after I've done that, and if I solve that to optimality, and you see the objective function doesn't even depend on these additional variables, then I can simply throw away x4, x5, and x6, and I have my optimal values for x1, 2, and 3. Okay, now I want to reformulate this yet again, because I now realize that I have more variables than I have equations. So that means that I can eliminate 3 of the variables. So I got a system of 3 equations, and okay, in this case, they're linearly independent. If that weren't the case, then I could throw away some of the equations. Fine. That's not a big problem, but let's assume that these are linearly independent equations, then I can actually eliminate 3 of these variables, and simply by how I formulated my equations, it's easiest to eliminate x4, 5, and 6, because then you just take the other variables to the right-hand side, and I can express this relationship by these 3 equations. And then I can also write z for the objective function and say, well, that's 0 plus, 5x1 plus 4x2 plus 3x3, my objective function. I'm cognizant of the fact that my variables must all be non-negative. And I don't have to kind of keep writing this as we go along, because it's easy to keep in mind. The thing that will change is this representation. But this is very simple. We have essentially 3 independent variables that we can choose. Well, not completely independently, because we must choose them in a way that makes x4, 5, and 6 non-negative, because we've got the non-negativity constraints. But as we can see from this representation, if I chose x1, x2, x3 equal to 0, then x4 would take the value 5, x5 would be 11, and x6 would be 8, and certainly they are non-negative. So that would definitely be one possible way of selecting my decisions. And then I could also read off what the objective value is, because having expressed the objective value solely in terms of x1, 2, and 3, which I can do, because even if it were dependent on x4, x5, and x6, since these are functions of x1, 2, and 3, I could substitute in and therefore express z solely as a function of x1, 2, and 3, the independent variables. So I can immediately read off what happens if I set x1, 2, and 3 equal to 0, then z is equal to 0. My objective is equal to 0. Okay, so far so good. We have a representation of our problem, and we can read off one particular solution, but probably not an optimal solution. And this is where it becomes interesting. Of course, we have not just one choice of variables to eliminate. We could have chosen a different set of variables to eliminate and come up with a similar representation. And perhaps this other representation also reveals a particular solution, and maybe that solution is better, i.e. our objective function would be larger, because we want to maximize the objective function in this case. And now the simplex algorithm is simply a way of systematically moving from representation to representation to representation, and each time improving the representation with regards to the objective, right, that we want to achieve, that is to maximize z. So if I look at this, and this is now the key. If you understand this, you understand the simplex algorithm, you can reconstruct it even when you're in your 80s and you haven't used it until then, because you just reinvent it. I see that if I increase x1 away from 0, and I'm allowed to make it positive, not negative, but positive, then that would increase z. So I don't want to keep it at 0. I want to make it as positive as I can. What keeps me from making this x1 too positive is, however, that x6 at some point will become negative. You see, you've got a negative coefficient here. So certainly I can increase x1 until it reaches the value 8 over 3, right? But not beyond that. So this equation, together with the inequality constraints and non-negativity constraints on the decision variables, impose an upper bound to the amount by which I can make x1 positive. And of course, I can also get an upper bound of 11 over 4 from this equation, and an upper bound of 5 over 2 from the first equation. And as it happens in this case, this first equation imposes the most restrictive of these upper bounds. So therefore, I can increase x1 to the value 5 over 2. What happens then is that x4 becomes 0. And so instead of eliminating x4 and expressing it as a function of x1, x2, and x3, I would like to eliminate x1 and express it as a function of x4, x2, and x3. Thus, interchanging the roles between x1 and x4. And conveniently, x4 then is 0, and so it actually fits with our interpretation of this representation of our LP as revealing to us a particular solution which is obtained by setting the variables on the right-hand side, which are called the non-basic variables, to 0, and then reading off the value of the so-called basic variables in this first column. Okay, so that's what we're doing. We see that 5 over 2 is the most restrictive of these upper bounds. And now we say we simply have to write x1 as a function of x2, x3, and x4, instead of expressing x4 as a function of x1, x2, and x3. And then, once we have this expression, we go back into this representation and replace x1 everywhere on the right-hand side by this function of x2, x3, and x4. And thereby, we express all these right-hand sides as functions of x3, x4, and x2, right? So I do that, and I get this new representation. This is, together with the non-negativity on all the variables, it's just another representation of my same problem. It's a bit of abstract nonsense, right, to write down the same problem multiple times. So what's the point of it? Well, the point is that if we set x2, x3, and x4 equal to 0, we reveal that the non-negativity of that first column reveals what values of x1, 5, and 6 we should choose to make this a feasible solution, and we can read off the objective value that this solution takes. So that is a valid choice of decisions, and it achieves an objective value of not 0, but 12.5, which is much better than what we had before. Right, so since this was so successful, let's carry on. Right? Would I want to increase x2 away from 0? No, I actually have no incentive to do that, because if I make epsilon, x2 an epsilon, a positive epsilon, I will lose some of my objective value, so I want to keep it at 0. Maybe later on, as I keep doing this, the situation changes and I will get an incentive to make x2 positive, but certainly not at the moment. But x3 is a variable that I would like to make positive. And then, again, I have certain entries with negative coefficients in this column, which then impose an upper bound on by how much I can increase the value of x3. Note that in this case, the second equation doesn't impose such an upper bound. So it's not necessarily the case that all equations in these representations impose upper bounds. So from the point of view of the second equation, I might as well increase the value of x3 beyond any bound. Right? So in this case, I only get two upper bounds, 5 and 1. 1 being the more restrictive of the two, means that I now need to represent x. So is it? So it comes from here. So instead of representing x6 as a function of x2, x3, and 4, I want to represent x3 as a function of x2, x4, and x6. And so then substitute again, and I get another representation of the same LP. Now I look at this representation and I see again that if I set my non-basic variables to 0, all my basic variables are non-negative, so therefore that's a feasible solution, and I can read off what the associated objective value is, 13. However, there's more to it in this case, because now I also see that all of these non-basic variables have negative coefficients in front of them, or non-positive. And that means that I don't want to increase any of these functions. You know, whatever I do to these values, the objective function as a function can be expressed in terms of these three variables only, because I used elimination in my equations. And you can see from this last line that the best values that I could choose for x2, x4, and x6 from the point of view of maximizing z would be to set them equal to 0. So therefore, I have a proof of optimality of the associated solution. So 13 must be the optimal objective value, and it can be achieved by setting x2, 4, and 6 to 0, and setting x3 to 1, x1 to 2, and x5 to 1. Right. So this was kind of a special example, particularly easy example, but you can generalize this to arbitrary LPs, and this is a very successful methodology for large-scale, even large-scale LPs, particularly if you have sparse data matrices. So, but from the point of view of implementations, this thinking in terms of these linear equations and changing the order of elimination is not the right way of thinking about it. So, yeah.
Just to make sure I remember things correctly. So it's a polyhedron in 6 dimensions. So on a vertex, there's 6 tight constraints, right? And since there are 3 equality constraints, that means that at every vertex, there are 3 variables equal to 0. So in this
Yes.
case, yeah.
Yes. Exactly. Yeah. So you're in an R6, right? So a positive ortho in an R6, and then you slice through that with an affine plane, right, of dimension 3, because you eliminate 3 variables. And that gives you a polyhedron, exactly. Yeah. And at every vertex, there are 3 variables that are equal to 0. And what we are essentially doing, another way of thinking about it geometrically, is we move from vertex to vertex along an edge, right? So, yeah. Right. So this interpretation of the simplex algorithm, as we've seen, can be reformulated in a way that's called the tableau format, which is probably the format in which, or the methodology that you've seen when you studied linear programming, and most people have. But it's really very much the same thing. It's just representing it in a different way. So you look at this, it's called a dictionary, and you say, okay, let's take all of the x data to the left. So I keep my vector of 5, 11, and 8 on the right, and then I write what's called a tableau. So simply, in matrix form, I write what the indices are, or the coefficients are, with which I have to multiply the vector x1, x2, x3, etc., x6, to get the expression which I obtain by taking this to the left-hand side. And I do this to the last line as well, and I multiply that by -1. So because these guys get taken to the left, I find -5, -4, -3, and then I multiply by -1. What's interesting in this representation is that you see that the eliminated variables, right, they can be identified in this tableau by the appearance of a unit matrix, identity matrix. Somewhere inside this tableau you find an identity matrix, which is here, which identifies x4, 5, and 6 as being the basic variables. And then the basic variables have associated coefficients in the representation of the objective function of zeros, because they don't appear here. And so if we change our mind about a choice of elimination, right, say instead of eliminating variable x4, we want to eliminate x1, then we can achieve that by dividing this whole line by 2 and then eliminating the 4, the 3, and the 5 in the lines below by subtracting the appropriate number of copies of this first line from these other lines. And that's exactly the same operations as we performed before, but expressed in a way that is easy to implement. It's called a pivot. Okay. So by moving from the first dictionary to the second dictionary, essentially what we've done is we've divided this first line by 2. So we identified first an entry in this last line that's positive, so a variable that we'd like to increase, a non-basic variable that we'd like to increase away from 0. Then we need to seek out all the coefficients that were negative in this dictionary above this number, but remember we took everything to the left-hand side, so negative entries become positive entries. So we pick out all the positive entries, and we divide these right-hand sides by these positive entries, take the least of these upper bounds, and that gives us a pivot. That tells us which entry we want to make a 1 by by dividing this line by this entry and then eliminate everything below it. And so if you do that in this tableau, you end up with this new tableau, which now has an identity matrix hidden here, here, and here. And that corresponds exactly to this dictionary that we constructed before. You can do it again with the third dictionary and so on. So here, first I identify a variable that I want to enter the basis by picking an entry that's positive. Then I'm looking at all these entries, these coefficients in the column. I take the right-hand sides, divide by the corresponding entry in this row if it's positive. I take the least of these upper bounds. That identifies my pivot. Now I divide this line by 2. I get this line, and then I simply eliminate all of these numbers. I want them to become zeros. So I subtract 4 times the first line from the second line. That gives me this new line, 3 times the first line from the third line, and so on. So that's the simplex algorithm for LP. Another concept that we need is LP duality. And LP duality is really conceptually just a way of generating upper bounds in the case of a maximization problem. So as we will see, branch and bound and these divide and conquer strategies that we will develop are based on better and better approximations of an initial integer programming problem by inclusion of extra cuts. So we have extra inequalities that we apply, and each time we need upper and lower bounds on the optimal value of certain subproblems of so certain IPs, smaller IPs. And so the way this is achieved is by what's called dual bounds. And this is really a copy of this concept of LP duality from the LP case. So if I were given this LP, which is exactly the example that we studied at the outset, and I was tasked to find a lower and an upper bound on the optimal objective value. And maybe if I have good bounds, I may not even have to then solve my problem to optimality, because I might see that these bounds are very close to each other and I'm very close to an optimal solution and I'm happy with the solution that I found. How would I get a lower bound? Well, conceptually, what I have to do to get a lower bound, a so-called primal bound, is I need to find a feasible solution. Right? In this case, I might find that x1 and x2, taking the value of 1 and x3 equal to 0 is a feasible solution, and this gives me an objective value of 9. So conceptually, although not necessarily algorithmically, it's an easy thing to generate lower bounds. But how would you generate upper bounds? How would you do that? We can focus on a simple example. For example, you look at this first constraint, and you know that no matter how you choose your objective, your decision variables x1, x2, and x3, they will have to satisfy this inequality. And also, they must be non-negative. So now if I multiply this entire constraint by 3, I get an equivalent constraint that reads 6x1 plus 9x2 plus 3x3 is smaller or equal to 15. But you know that if x1, 2, and 3 are all non-negative, then 6x1 will be greater than 5x1, 9x2 will be greater than 4x2, and 3x3 will be greater than 3x3. So therefore 15 must be greater than 6x1 plus etc., which is in itself greater than 5x1 plus 4x2 plus 3x3. And since it's true for all feasible vectors, x1, x2, x3, 15 must be an upper bound. 15 doesn't depend on these decision variables must be an upper bound on the optimal objective value that I can achieve. In fact, we've just solved this particular LP instance to optimality, and we saw that the optimal solution was 13. So it's reassuring to see that it works. Now, so this I spelled out here. We can do other manipulations as well. We can say, let's take the first two constraints and we add them up. You know, if I have the sum of these two constraints, I find that 6x1, which is greater than 5x1, plus 4x2, which is greater than 4x2, x2 being non-negative, plus 3x3, which is greater than 3x3, x3 being non-negative, must be smaller or equal to 16. So therefore, 16 must be an upper bound on the optimal objective value. Can we generalize this? Yes, we can, because if we look at the constraint matrix and we take non-negative multiples of these rows and add them up in such a way that component-wise these coefficients become greater than the components in the objective value, in the objective function, then it must be true that the same linear combination with these same linear weights of the right-hand side vector must become an upper bound on the optimal objective value of the original instance. And so having identified a general rule for generating upper bounds, we can say, well, what's the least such upper bound? Clearly, as we can generate not one upper bound, but many upper bounds, we want to find the least such upper bound, the best such, tightest such upper bound. That then leads to another optimization problem, which is to find the best such upper bound. And that's called the dual of our LP. So what happens is that the objective function has coefficients that were previously the right-hand side vectors. The new right-hand side vector consists of the coefficients of the original objective function, and the constraint matrix has been transposed and the inequality signs have been reversed. And the maximization has turned into minimization. You can do this for more general problem instances. So if you have a situation where you have a bunch of equality constraints and inequality constraints, and only some of the variables are bound constrained, then you can also set up a dual in much the same way and derive it in much the same way. So what you see here is that essentially for every primal constraint, we end up with a dual variable. And if the primal constraint is an equality, then the dual variable is not bound constrained. If the primal constraint was an inequality constraint, then, however, the dual constraint will be bound constrained. And for every primal variable, we get a dual constraint. And if this primal variable was bound constraint, then the dual constraint will be an inequality constraint. And if it was not bound constrained, as for these variables S, then the corresponding dual constraints will be equality constraints. It's an easy exercise to go through the motions of setting up the dual of this using much the same logic as I applied to derive it in the case of our example. But this is how you derive the dual. Now, we already know that the dual gives us a valid upper bound. So we start with a primal problem that's a maximization problem, and the dual is a minimization problem. We know that this gives us an upper bound. So the optimal value of the dual will be greater or equal to the optimal objective value of the primal. However, it's the strength of this LP theory, right? Arises through this LP duality theorem, which goes back to von Neumann, which shows that when you solve to optimality, when you solve both problems to optimality, then generically, they take the same objective values. So there's no gap between this upper bound. It becomes so tight that it matches exactly the primal bound. Associated with this proof, which we will not go through, but you can actually use the simplex algorithm itself as a mechanism to prove this theorem. That's the easiest way of doing it. And out of this particular proof comes this additional theorem, which is complementary slackness theorem, which says that if there's a finite feasible solution of P, then such a solution is optimal if and only if there exists a particular dual optimal solution Y star that satisfies these following conditions. So here I'm looking at a situation where I only have inequality constraints and bound constraint variables. So all my primal constraints are inequality constraints, and the variables are bound constraints, so constraint be non-negative. So what this theorem says is that whenever one of these variables, for all of the variables in my solution that are strictly positive, the associated dual inequality constraint must hold as an equality. And for any dual constraint that doesn't hold as an equality, for any primal constraint that doesn't hold as at equality, in other words, it's not active, what we call active, the corresponding dual variable has to be equal to 0. Now this seems like a technicality, but it's actually hugely important, because it means that if I give you x1, etc., xn, and I claim that this is optimal, you have an easy way of checking that it is without having to optimize the whole problem. Because out of these conditions comes a m by m linear system that you need to solve in order to generate your dual solution. Once you have this dual solution, if it does exist, if I'm right in claiming that x is optimal, you can check if the associated dual objective value is the same as the primal value. So this is, in fact, the mechanism that renders LP a problem that is in NP. So it's polynomial checkable. Now we know that it's also solvable in polynomial time, but that wasn't always the case. So let's quickly see how this works. If we go back to our problem, and I give you the solution, x1 is equal to 2, x2 0, and x3 is equal to 1. And you haven't seen my solution of the simplex algorithm, so you don't know if I'm bluffing or if this is true. Right? I say, I claim, I've done my work, this is the optimal solution. How can you check that easily? Well, you see that, first of all, two of these variables are strictly positive, right? x1 and x3. And therefore, we know that two of these dual inequalities must hold as equations. So immediately, I can identify that. There's the two of my dual inequalities, the corresponding inequalities, which I now can write as equations. But I can also use this bit here, namely by checking my vector x. I find that that this second constraint is actually slack. As the left-hand side is 10, which is strictly smaller than 11. That gives me the information that the corresponding dual variable must be equal to 0. So although it looks as though I had, actually, in fact, I do have a linear equation, system of linear equations with 3 unknowns, I'm given more information because one of these variables is fixed to 0. So therefore, I can eliminate it, and I end up with a 2-by-2 system, which I can solve, and I get my dual solution, which I can now substitute back into the dual objective value, and I can check that its value is also 13, and therefore, I have to admit, the solution you give to me was optimal. right? Okay. Right. I think we have a scheduled break in 3 minutes, but maybe I'll. Yeah, I'll just do my 3 minutes, and this would be a good place to break. But anyway, now let's go back to integer programming, right? So we want to solve integer programming problems, and we know that these are much harder to solve than LPs because of the integrality constraints, and that imposes some kind of combinatoriality. So branch and bound is not just one algorithm, it's a kind of a whole framework for constructing algorithms that's quite nice because it has this kind of flexibility of kind of modularity to it, in that you can use different mechanisms for generating dual bounds, i.e. upper bounds in the case of optimization problems that are maximization problems, and primal bounds. And also certain other choices. So it is a kind of flexible framework that you can adapt to many different specific problem classes. But what we will discuss now is an approach that works generically, because we've seen that every integer programming problem has an LP relaxation. So you can always say, let's give up on the requirement that our variables are integers, right? And then by giving up on these constraints, I'm allowing myself to look at a larger set of decisions. If I maximize the same objective function over these larger sets of decisions, then what happens is that I'll end up with a larger objective value, which then is an upper bound on the optimal objective value over the original set that I was looking at. So therefore, that generates a dual bound. So branch and bound is a kind of divide and conquer strategy. So imagine that you have your original set F, which you can think of as the enumeration of all the feasible points of your original IP, right? And if I break this into smaller sets, and I write this as a union of smaller sets, which themselves are feasible sets of other IP problems. And if I maximize that same objective function over each of these smaller sets, and I call set J the optimal objective value that I achieve over each of these, over the set Fj, then surely the optimal objective value of the original problem would have to be the largest of these objective values over the subproblems. Why? Because the optimal vector of decisions, being an F, lies in the union of these, must be in one of the Fj's, right? And must, achieve set J, right? Oh, good. So this is a trivial proposition, but it's sort of what everything else is based on. I think we'll now take our break, and then we'll look at an example and carry on this thought. So this is a divide and conquer strategy that subdivides a complex, large, feasible set for a difficult problem into smaller sets which are easier to deal with. And here, just conceptually, I want to give you another example. The model doesn't matter so much, just in terms of explaining what's going on in this divide and conquer. This is the traveling salesman problem. So it's the problem of a salesman that has to go and visit every city of a network of cities exactly once. So starts maybe from his home city and goes and visits these other cities in such a way that they arrive at each city exactly once and leave every city once because they don't want to go back to a place they visited before. And there are mutual distances between city I and city J given by Cij. So what they want to do is minimize the total distance traveled. So what we have here is a model with some binary variables xij that are essentially flag variables. Xij is equal to 1 if the path from I to j, that leg, lies along the tour that they take. and 0 otherwise. So these are simply flag variables, indicator variables that tell us which of the legs we take. But of course, we need to write down some constraints that make sure that the salesman only goes to each city once. And so this first set of constraints just says, well, we'll arrive in each city exactly once, and then we'll leave each city exactly once. And what makes this a complicated problem, in fact, an NP-hard problem, is the this type of constraint here, which tells us that you really want to have a solution that kind of looks like this. Every city lies along this path, rather than this type of solution where you have a subtour on a set of city S and a subtour on another set of cities, maybe multiple subtours. And so what it simply says is that for every set S amongst the cities, so for example here, this set S, if you pick, if you look at all the nodes I, all the cities I in set S, and all the cities J in the complement set, there must be at least one of these legs from a city I to a city J that's occupied, because otherwise this is disconnected. So, yeah. So these are so-called cut set constraints. And unfortunately, there are a lot of these constraints, right? There are a lot of these constraints because you have combinatorially many subsets S that you can choose. So here it's depicted again. This is just you fly from city I to city J and so on. Now, the reason why I mention this problem is because we can sort of conceptually say, how would we divide our set of feasible Hamiltonian tours into subsets? Well, you could distinguish between tours that start in a particular way. Say I have, I'm looking at the set of all Hamiltonian tours on 3 cities, or 4 cities, right? And it doesn't matter where I start because I go and visit every city once. So I could say, without loss of generality, I start in city 1. But then I have to go somewhere first. And this could be city 2, it could be city 3, it could be city 4. So basically, my set of feasible solutions splits into 3 subsets, which I call here F12, because this is the set of tours that start with the first move from city 1 to city 2 and then finish off somehow. F13, which make their first move to city 3 and then finish off the tour somehow. And F14, which are all the tours that starts with a move, from city 1 to city 4. Okay, and each of these sets can be further subdivided. So for example, F12 can be subdivided into F1223 and F1224 because depending on how I take my next move, right? And you can see that once you're down at this level, in this case, on traveling salesman problems on 4 cities, the remaining moves would be fixed because they have to go to city 4 and then back to city 1. So if I split my set F into these 3 choices and then each of these gets split into 2 choices, I end up with singletons down here. Each of these sets have only a single point. And of course, it's completely trivial to optimize an objective function over a set that contains only one point. Just evaluate the objective function at this point. And it seems that this is all useless because what I'm proposing is essentially a complete enumeration of all the points in this discrete set F, which we know is very quickly impossible in the case of the traveling salesman problem because it has exponentially many possible tours as a function of the number of cities. So branch and bound clearly is something more complicated than this, but actually it doesn't need much more. The only thing that we need is we keep in mind that we conceptually do this. We conceptually split this feasible set into smaller and smaller problems to the point where perhaps deep down in this tree we have singletons. But we hope never to have to go there. And the reason why we never have to go there and the reason why we never have to develop this entire tree is because we will compute at every stage upper and lower bounds, primal and dual bounds, on the optimal objective value that we can achieve over these sets. And in doing so, we may discover that some of these sets will not have to be developed. So we hope that a large part of this tree will never have to be generated. That seems abstract at the moment, but you will see in the next few slides that actually it's very concrete and it can be done quite easily, conceptually quite easily. So upper and lower bounds, why are they interesting? I mean, we need to understand how they help us eliminate parts of this enumeration tree. And this is a very simple proposition. It's a one-liner, it's a one-line proof, but basically what it says is this. So again, imagine that we have our feasible set and it's split into k subsets. And I have, for each of these subsets, I have, and here I'm maximizing, so I have an upper bound, which I call a dual bound, right, on the optimal objective function, optimal value of C transpose X over the set of X in the set Fj. I've got this upper bound, set J being the optimal value, right, achievable over the set Fj. And then I've got a lower bound as well, which is essentially, there's a primal bound. Just need to find a feasible solution. Need to find a point in Fj and evaluate the objective value, and that gives me a lower bound. So if I have a mechanism to generate upper and lower bounds on set J, the optimal objective value of this objective over each of these sets Fj, then these upper and lower bounds give me upper and lower bounds on Z, the optimal value of my same objective function over the original big set. How is that? Well, I claim that a lower bound on Z is given by the maximum of the lower bounds, right? And an upper bound is given by the maximum of the upper bounds. So in both times I need to take the maximum. Why is that true? Well, for every j, it will be the case that Z, this global maximum, this maximum over all the x's in F, must be greater or equal to Zj, the maximum achievable only over the subset Fj, and that is greater than the lower bound, Zj lower bound, on this. So therefore, since the said lower bound j's are smaller or equal to Z for all j, the maximum of these must also be a lower bound on Z. So that's easy to understand. So Z is greater than the maximum of these lower bounds. And furthermore, Z itself is just the maximum by the proposition that we saw before the break of the set J's, because the global optimum must be in one of the sets Fj, and that itself is smaller than the maximum of these upper bounds set J, because it's smaller than set J upper bound. So therefore, the maximum set J upper bound will be an upper bound on Z as well. Okay, the reason why this is interesting, I mean, this is completely trivial, but it's interesting, means that if you have a mechanism for generating primal and dual bounds in each of the constituent sets Fj, then you can find new upper and lower bounds, maybe have an a priori upper and lower bound on F, but by doing this, you can tighten these upper and lower bounds. And if you keep doing this, you get tighter and tighter bounds, the upper bound coming down and the lower bound coming up. It sandwiches the optimal value, right, in an interval. And if this interval is small enough, you can say, I'm happy to stop here. Or if the interval goes down to 0, you have a proof of optimality. And that is good to know, but doesn't explain yet how we can avoid having to look at certain branches of this tree. It still seems at the moment that we need to develop the entire enumeration tree. But there are 3 mechanisms that we can use to prune entire branches of this tree. That is to say, we don't have to develop them. The first is pruning by bound. So imagine you start with the master problem. This is the original problem. And you generate an upper bound, for example, by LP relaxation. You generate a lower bound, for example, by finding a feasible point. So upper bound of 36, lower bound of 20, you know the optimal value is sandwiched between the two values. Now you split F into two subsets, F1 and F2, and you do the same for those two subproblems. Find upper bound of 33, lower bound of 25, and here an upper bound of 24 and a lower bound of 21. Using the previous proposition, the proposition from the previous slide, we can now tighten these bounds, replace the 36 by the maximum of 33 and 24. And this lower bound of 20 can be tightened by replacing it by the maximum of the two lower bounds on F1 and F2, which is 25. Well, once I've done that, I can now see that the optimal solution to the master problem could never be found in this branch. It cannot be in F2 because the maximum achievable objective value for points in F2 is 24, yet I'm guaranteed that I can find an objective value of at least 25 over the original set. So the optimal decision cannot lie in F2. It would have to lie in F1. So we hope that this mechanism allows you to cut off branches early on and avoid having to develop a large part of this enumeration tree. So that was the first elimination or pruning mechanism, is pruning by bound. The second mechanism would be pruning by infeasibility. If it turns out that one of the feasible set of one of these sets, Fj, is the empty set, then obviously you don't have to explore it any further because there are no points there to consider. However, it may seem trivial, a trivial remark that you can do this, but it's less trivial to detect that a feasible set is empty because feasible sets are defined in terms of constraints. So they're defined implicitly, not explicitly. We're not given an explicit enumeration of the points in this set, but we're given a set of constraints, and we say, let's look at the sum total of points x decisions that satisfy all of these constraints. So by looking at these constraints, you have to do something algorithmically to detect or to prove that the set is infeasible. Specifically, if it turns out that the LP relaxation, which has a larger set than Fj, is an infeasible problem, that it has an empty feasible set. And that is a situation that you detect using a refinement of the simplex algorithm as I introduced it. So there's more to it, a lot more to the simplex algorithm we said. One of the strengths is that it detects when a feasible set is empty. Then Fj itself must also be empty. And then the third mechanism is pruning by optimality. If it turns out that you've identified an optimal solution on this set F2, for example, then even though I tighten these bounds using proposition 2, and I have a lower bound of 27 on F, and here I found a solution that achieves 27, it's an optimal solution for F2, I then no longer have to look at F2 any further. I don't have to split it. I already found the optimal solution over F2. This may very well turn out to be the optimal solution for the whole set F, so I'm not throwing away that solution. I'm always keeping the best solution encountered so far in memory. This is called the incumbent, which may later be discarded if I find a better solution over this set, which has the potential to give me a better solution yet. Okay, so now putting these elements together in a systematic way, we have an algorithm. So what we want to do is we want to implicitly build an enumeration tree by subdividing the feasible set of the master problem into subsets. Exactly how we do that we need to discuss on the following slides. And there are many ways of doing this. further down in the branches, we can apply that same mechanism to split the fj's into further subsets, right? And then we hope that we only need to build the parts of the decision tree that actually need to be explored, that are worthwhile exploring, and that this is a small part of the entire tree. And the reason why we can do that is that for each subproblem we generate dual and possibly primal bounds, but the dual bounds are more important. And in our case, we have so far only seen one mechanism for generating dual bounds, and that's by LP relaxation. You give up on the integrality constraints, thereby enlarging the feasible set. You optimize over this because now you've got an LP problem and you know how to solve these using the simplex algorithm. And bingo, you have an upper bound. Knowing these upper bounds and possibly knowing lower bounds, we can use tightening using proposition 2. That gives us upper and lower bounds that get tighter and tighter on the master problem. And every time we tighten these bounds, we can then go into the branches again and check what the upper bounds on these branches are, and thereby start discarding some of the branches. So you put it all together and you end up with this kind of pseudocode where you start with a set of, maintain a list of active nodes. So these are subproblems you haven't explored yet. You haven't computed upper and lower bounds yet, and you haven't split them into subproblems. Initially, this is just a master problem. You can think of this as just being the feasible set. If I identify the feasible set, I'm identifying the subproblem that I'm looking at because the objective function doesn't change. It's always the same. And I have an a priori lower bound of minus infinity and a priori upper bound of plus infinity, and my incumbent is just the empty set. I don't have any incumbent. And then while I have nodes that haven't been processed, so while this list is non-empty, I pick one of these nodes and I process it. Perhaps I already have some bounds lying around later on in this iteration. I will have some bounds to propagate, then I propagate these to the master node and or the root node, and I get tightened upper and lower bounds. And this is important because I want to discard parts of the branch. But initially, I can't tighten anything. So I choose a subproblem from the list of active nodes, and then I compute a dual bound, set up at bar j, using LP relaxation. And if this happens to be smaller than the lower bound on the master problem, then I can prune by bound. I can discard this entire branch. Otherwise, two things can happen. Perhaps the feasible set of my LP relaxation is empty, in which case I can prune this branch by infeasibility because fj will be empty as well. Another situation that can happen is that the LP is unbounded, in which case I need to branch it. So I remove fj from the set of active nodes and I split it into two. Or most of the time, the LP relaxation has a finite optimal solution. I look at this arg max, the optimal solution itself. I check, is it feasible? Does it satisfy the integrality constraints? If it does, then it might be the incumbent. I need to compute the objective value that's associated with it and see whether or not that gives me an objective value that is larger than the previous lower bound on the master problem. If that's the case, I replace my incumbent by xj. This is a better solution. I keep that in memory. Otherwise, I can prune this subproblem by optimality. This is I'm still in this if statement. That's considering xj, the optimal solution to the LP relaxation of the jth subproblem was integer feasible. Then since I solved this to optimality, then I can prune this subproblem by optimality. So I use one of the third pruning mechanism. And otherwise, and I'm in this situation where my solution is not feasible, but I solve the LP relaxation to optimality, and that gives me an improved lower bound, and I can split my problem into two subproblems and propagate the bounds. So how do I split a problem into two subproblems? This is not explained yet, but we'll now see an example that makes this clear. It gives us a general mechanism that is not always a good mechanism, but it's a mechanism that gives you an idea of how this can be done for a general problem. So let's look at this problem, which is easy to interpret geometrically because it contains only two variables. So you can immediately see yourself what the optimal solution is, but the point here is that we want to apply branch and bound to solve this. So two integer variables, x1 and x2, and the feasible set is constrained by these linear inequalities, and this is our objective. So first we need a dual bound, so we give up on the integrality constraints. We just say x must be non-negative. We end up with an LP. And introduce slack variables, do all the business of the simplex algorithm that we discussed before, and we find an optimal solution for this LP subproblem given by 20/7 and 3. Okay, this is definitely a finite optimal solution to the LP subproblem. Is it integer feasible? No, because the first variable happens to be fractional. So we haven't found an incumbent yet. But now we can look at this solution and we say we have an upper bound, which is 59/7, the optimal objective value of the LP relaxation. And this information gives us a way of splitting our feasible set, because we know that x1 must be integer, and so therefore it must be either smaller or equal to the floor of 20/7 or greater or equal to the ceiling of 20/7, the rounded up value of 20/7. So that's the key here. I can split f into two subproblems, f1, f2, given by one additional constraint. Right? One is saying that xj, my fractional variable, in our case x1, must be smaller or equal to the rounded down value of this fractional value that it takes under the optimal LP solution, or it must be greater or equal to the rounded up value. So in our case, f1 consists of rounding down this value to 2, and so we have this additional constraint that x1 is smaller or equal to 2. And likewise, for f2, we have a new constraint, x1 is greater or equal to 3. Still imposing the integrality constraints. Now the beauty of this is that if I now look at the LP relaxations of these two problems, and I find new upper bounds on f1 and f2, these upper bounds will be strictly lower than the upper bound of 59/7 that I achieved before. Why? Because in order to achieve 59/7, I would need to be able to take these values, 20/7 and 3 for x1 and x2, which are now excluded because I cut out a corridor from the feasible set. So imagine I have a feasible set like so, and this is the optimal solution. There's an optimal solution to this LP relaxation that's somehow here. Now I'm cutting out the corridor and I say, well, this is my f1 and this is my f2. Well, this solution is cut out. It can no longer be achieved. So next time I compute an LP relaxation of f1, it will get an optimal objective value that's strictly smaller than my 59/7. Yeah. Likewise over f2, and that means that as I keep propagating these upper bounds, they monotonically decrease, and likewise the lower bounds will monotonically increase. And of course, hopefully at some point, upper and lower bounds will meet. Okay, so I've got my two subproblems, f1 and f2, right? And now I'd like to pick one of these two problems to, so far I had this 59/7 upper bound, lower bound is still minus infinity. By the way, in this case, the objective value or the objective function of this master problem has integer coefficients, and I know that x1 and x2 must be integers. Immediately, that means that I can round down this upper bound, and I still have an upper bound. And so I'm so far in this situation where f got subdivided into f1 and f2 by inclusion of these two separate additional inequalities. I can now say this node has been processed, and I've got my set of active nodes, which are f1 and f2, and I can pick one of these nodes arbitrarily. So let's pick f1, for example. And so we see that we again look at the LP relaxation of this problem, and this time what happens is that it differs from the LP relaxation of the master problem by inclusion of this extra constraint. There's only one extra constraint that was involved. Well, it turns out that one can warm start the simplex algorithm in this case. We don't have to start pivoting from the start, not knowing, as if we didn't know anything about this problem, but we can warm start using the optimal tableau of the previous problem, and this is using something called the dual simplex algorithm, which I didn't have time to introduce today, but essentially it means applying the simplex algorithm to the dual, because we saw that on the strong duality, the dual and the primal achieve the same objective value at optimality. And so there is a way of turning primal optimal tableaus into dual optimal tableaus. And as it turns out, if you introduce an extra constraint in the primal, that means that you introduce an extra variable in the dual, and you can extend your previously optimal dual tableau into a dual feasible but suboptimal tableau, which you can continue to pivot on, and usually after one or two pivots it's optimal again. So I'm not going into the details of this, but the sources that I indicated at the start of this lecture will give you a lot more on this. But in any event, you then solve this to optimality, taking, in this case, one additional pivot, and you find this optimal solution of 2 1/2. Again, you have a fractional variable that you can use to branch this set F1 into two subsets, F11 and F12, in this case by inclusion of these one additional inequality, x2 smaller or equal to 0. We also know it's greater or equal to 0, so it must be equal to 0, or x2 greater or equal to 1. And now you have a new upper bound, 15/2, the optimal value of this LP relaxation, which you again can round down, and then you can propagate these bounds, and I'm not going to go through the rest of this problem, but if you download the lecture notes, you will see how this is done. Yeah. Basically, after a few iterations, you can prune some of these sets by optimality. You can prune others by infeasibility, and you can prune some by bound. So in this case, you see that although you haven't resolved this part of the branch, the best value that you could possibly achieve here is an upper bound of 7, but you already found an incumbent of 7, and the minute the upper bound and the lower bound on the master problem match up, this gives you a proof of optimality of the incumbent, and you can stop. Okay, so I'll now move on to the theme, right, of this this series of lectures, which is how to exploit partial decomposability of very large-scale integer programming problems. And so this relies on applying the Simplex algorithm to extremely large-scale LP problems. They're so large that you cannot keep the constraint matrix A in memory. So you don't want to generate the entire constraint matrix. The beauty of the Simplex algorithm, which we haven't, or one of the beauties, which we haven't discussed, is that you only ever need the columns that you needed for a particular sequence of pivots you used so far. So there are parts of this matrix that are there, you know that they're there, but you don't need to know explicitly about them until the point comes where you would like to increase the corresponding non-basic variable away from 0, because that would allow you to make progress. And so what we will see is that is a technique that allows you to work with only the columns that you need so far, in the pivots that you take, and then when you need a particular column, you need a mechanism for detecting what this column is, and you then generate it. That's why it's called delayed column generation. And it relies on the so-called Danzig-Wolff reformulation of IPs. And this is possible for IPs that have specific structure. And so specifically what we're looking at is this kind of structure here. What I've done here is I've split my decision vector x into blocks, x1, x2, x3, and so on. So what we maximize is so C1, C2, etc., CK transposed into, here is a block x1, block x2, and these are block vectors, right? Block rows xk, and then subject to a bunch of equations and inequalities, and this has particular block structure as well, in that I have kind of blocks A1, etc., AK in the uppermost layer, if you will. And then I have a kind of a diagonal structure. So I have some other constraints that only affect one block at a time. So if you look at this, you have the sum of the kth block matrix AK with the kth block of X, right? The sum of these must be equal to right-hand side vector B. So here I have some equalities or inequalities. I've got first block B, and then I've got some other stuff. So these are the constraints that globally tie together all the decisions. But then when I look at each block, right, xk must be in a certain feasible set, which is in itself defined by here inequalities d1, d2, d3, etc. dk times xk must be smaller or equal to little dk, right? And so you see, because the objective function decomposes into functions that only depend on each of the blocks separately, and these constraints are completely decomposing the constraints, if only these annoying constraints of this block weren't there, I could just solve k subproblems independently, and they're of much smaller size because I'd only have to consider the blocks xk. So this is what we mean by partial decomposability. So, and this is also a structure that you find in continuous optimization problems associated with big data problems very often. That you have an objective that is a sum of very simple objectives that depend only a few on a few variables, and then you've got these sort of local constraints, and you've got a few constraints that tie everything together. And so solution techniques to solve such problems in parallel focus, or in a distributed manner, focus on sort of forcing these constraints that tie all the variables together to kind of relax these, update each xk separately in parallel, and then start exchanging information that allows you to, again, better satisfy these joint constraints. And the technique that we will discuss can be seen in this light, right? But it is intrinsically a technique that works for discrete problems, so with integrality constraints. So here you see each of these sets xk is actually a discrete set. I have integrality constraints on these x's, and then a bunch of linear inequality constraints. Now, conceptually what's going on is that each of these xk's, right, if you think xk is the intersection of some polyhedron, right, given by these linear inequality constraints, dk xk smaller or equal to a little dk, intersected with the integer lattice. Okay. So it's a discrete set, and if this polyhedron is compact, then this discrete set will be finite. So conceptually, you can think of xk as being enumerated. Of course, we hope that we never have to enumerate all these solutions, because it would be intractable. But let's say xk can be enumerated into a large number of discrete points, xkt. So this first coefficient k index just indicates which of these sets xk this point belongs to, and t is the variable that enumerates all the solutions in xk. Of course, each of these xk's has a different number of solutions, so therefore the number of solutions tk itself depends on k. So that's just a conceptual enumeration. We don't want to do that in practice. To make matters more abstract, or more abstract nonsensical, you could say you can now represent any xk in this set, capital Xk, as a linear combination of all of these enumerated points, xkt, with weights lambda kt, which must be either 0 and 1, and exactly one of which is a 1 and all the others are zeros. So that seems to be a fiendishly useless and complex way of representing this set. But it's definitely, you have to admit, a correct way of representing this set. It's not a practical way, but it's a way. And yeah, I mean, of course, this condition, right, that the sum of the lambda k's must be equal to 1, and they're all binary variables, means that only one of these lambda kt's is equal to 1 and all the others are equal to 0, and then you pick up exactly the corresponding xkt, which we know is in xk. So therefore, every point xk in capital Xk can be represented in this way. So, are there any examples of problems that have this structure? Yes, earlier we saw that the incapacitated facility location problem has this kind of structure. So this was the problem. That was the first IP that we wrote down, right? And so here I could subdivide these decision vectors, the decision vector of the x ij's and yj's, into blocks that fix a particular, that are associated with a particular location, j. And then I collect all the decisions as to what proportion of service, of the demand of each of the clients I want to service from this location. And I also pack the yk in. Right? And now I see that it's these constraints here that look at each customer individually and say, well, actually, the total demand of this customer has to be satisfied. I don't mind how, but somehow I have different contributions from different locations, but the total demand has to be satisfied. It's these constraints that somehow tie together my decisions that I take for the amount of service that I want to provide to each client from each of the facilities. So if these constraints didn't exist, then the problem would decompose into separate optimization problems at every location, at every facility location. So therefore, they form these, if you will, that annoying top layer of constraints in this overall constraint matrix. And in this case, it's simply this block. Each block consists of an identity matrix of size m and a zero vector, right? So now we can use this Danzig-Wolff reformulation. So I'm going back to kind of the general development of this this methodology. So we started with this master problem that we'd like to solve, and then we use this kind of inherent enumeration of these sets xk, and we represent them in a really awkward way. Well, it's not that awkward, but it seems very inefficient. But what we can do, since each xk has this representation as a linear combination of the constituent vectors xkt in the set capital Xk, we could go back into the master problem and replace xk wherever we see it by this linear combination. And I've done it here, and I expressed everything in terms of the lambda kt, which now become my decision variables. Right? So I could say instead of the x's, instead of deciding on xk, I can decide on the lambda kt's. Note that the xkt's, these are fixed because that's an enumeration of all the feasible points, although I hope never have to do it, but in principle, this is possible. And then I just need to decide on my lambda kt's. And of course, holding k fixed and summing over t, I know that these lambda kt's have to sum to 1, and they have to be binary variables, right? So that comes from basically this representation, this Danzig-Wolff reformulation. Right, so this is clearly an integer programming problem that is equivalent to the original master problem, but it seems still a bit awkward to do this because it has many, many more variables. And by the way, they're also binary variables, so they also have integrality constraints. And so it seems that perhaps we're not gaining anything. But in terms of solving the LP relaxation of our IP, we've gained a lot, as we will see now, because if we look at these constraints, and if we were to give up on the integrality requirement on lambda kt, that would then allow us to choose lambda kt between 0 and 1. And this requirement then would say, well, the lambda kts taken together for a fixed k just have to be the weights in a convex combination of these tk objects. So what we're looking at is convex combinations of these coefficients and these vectors. And that gives us the structure to work with. So here's another example. It's the UFL again, but this time I'm using the so-called weak formulation. So the difference here is that previously I had inequalities xij smaller or equal to yj. I've summed these, right, over all i's. And that still forces yj to be equal to 1 if one of the xj's is strictly positive. But then the second difference is that the x's themselves are binary variables. And this is, I mean, you can show that without loss of generality, the UFL, I mean, I'm looking at a more restricted set of solutions, but amongst the optimal solutions of the original UFL, the optimal solution to this problem will also be an optimal solution to the original UFL. The original UFL may not have a unique optimal solution, but the optimal solution to this problem will be optimal for the original UFL. So this is called the weak formulation. And so here my x's are all binary vectors, right? My y's are binary vectors. Again, I collect the same kind of groups of vectors. And now I'm looking at these constraints here, which tell me that for a fixed j, right, I'm only looking at these variables. I need these constraints here to be satisfied, these conditions to be satisfied. So that means that xk is the set of indicator vectors, right, for any subset of the set of M of clients, right? I need to choose, if I have, if I use this indicator vector, then I need to switch on, four. So if these are the clients that I'm fully servicing from this location, and this set S is not empty, then I need to switch this facility on. So I need to choose the corresponding y equal to 1. Only if this is a 0 vector, in other words, S is the empty set, can I switch this off. Of course, technically I'm allowed to also take this first vector to 0 and this last entry to 1, but that's not optimal, as we will see on the next slide. And so now I have an enumeration, right, of this xk, because I know it's all these indicator vectors that appear. And there's a large number of these. And associated with these, I have these variables lambda k for each of these columns, right, that vectors that I'm generating. I have a lambda k j, but here it's easier to indicate them or to enumerate them by or identify them with the subset S of clients that I'm servicing from this location j. So I'm writing lambda ks for the variable associated with this solution, And then for this particular solution here, I use a different variable, right, new k, because it plays a separate role. Right, so now we can use our Danzig-Wolff reformulation, and in this case we end up with this problem. So what happens here is the x's have disappeared. Why? Because they've been replaced by these xkt's, right? Each of which are indicator variables. So the binary variables that have zeros and ones. And where there's a 1, I pick up a Cij, and where's a 0, I don't pick up the Cij, and so in this sum, it doesn't appear. And I'm also then, for each of these, so long as S is non-empty, I pay the price of having to open, or if Yj is equal to 1, I have to pay the price of opening this this facility. So I'm counting Fj. By the way, here I'm minimizing the total cost because I'm thinking not in terms of a profit for Cij is not a profit for servicing client I from location J, but a cost. So you can take minus the profit, for example. And then there's lambda 0j, which is the silly situation where I do not service anyone from location j, but I build the location. I still pay the price, fj. And you can easily see that in an optimal solution, lambda empty set j would have to be equal to 0, so therefore you can discard it. Okay. Now, you end up with this very large integer programming problem because the lambdas are all binary variables. And you see you have combinatorially many of these variables for each location j. Because for each location j, I need to look at all subsets S of the clients, and usually the set of clients is much larger than the set of locations. So I get a huge number of these lambdas. Nonetheless, the requirement that for a fixed I, for a fixed client, if I sum over all the lambda js where I is in S, so all the then this must be equal to 1. So there will be a decision to service this client's demand from some location that I'm building, right? Anyway, I think maybe I'm skipping this example because this is taking you too much away from kind of the main strand of the theory. But there is a way of kind of artificially fitting the symmetric traveling salesman problem. That is the TSP, where flying from city I to J and flying back from J to I have exactly the same cost in that same framework. Right. So far, what have we achieved? Right. We started with a large-scale integer programming problem, which partially decomposed because we had this structure, that there's only one layer of constraints that ties together decisions that we could otherwise take separately over blocks of variables. We've got a bunch of other constraints that tell us how these integer variables can be chosen. If only that first layer wasn't there, we could solve everything in parallel and solve for the optimal solutions and compose the optimal objective value by adding the individual contributing terms, because the objective function itself also decomposes in this way by a contribution C1 transpose X1, and a separate contribution C2 X2, and so on and so forth. So that was our point of departure. And then using the Danzig-Wolff reformulation, which was based on an intrinsic enumeration of each of these sets xk, we ended up with this much larger scale, even much larger scale, binary integer programming problem, because the lambdas are binary variables. Okay? So now we can look at the LP relaxation of this problem. So we propose to use branch and bound on this reformulated problem. When we do branch and bound, or at least when we do LP-based branch and bound, as we've seen in the earlier parts of this course, we need to be able to solve the LP relaxation of this master problem. So I call it the LP master problem. This looks exactly like the master problem, except that I've given up on the integrality constraints of the lambdas. The lambdas are no longer binary variables, but they are variables between 0 and 1. The upper bound of 1 is not required, strictly speaking, because you see that each of the lambda k's appears in one of these sums, which itself must be equal to 1. Therefore, given that all the lambda kt's are non-negative, this imposes an upper bound of 1 on each of the lambda kt's. And if we look at this problem, we see that this is a very nice structure to work with, because this just tells me that for each fixed k, the lambda kt's ranging from 0 to tk, which is the number of discrete points that I have in the set capital Xk, must be the weights of a convex combination of tk many objects, right? And then what I see here is that I'm looking at this corresponding convex combination of certain vectors, column vectors, that I generate by multiplying this kth block of this constraint matrix with the specific solution xkt, specific point in capital Xk that is associated with the variable lambda kt. So these are all columns, right, that I need in principle, but I've got a huge number of these columns, and I would like to not have to generate them all, only the ones that I need, because it's completely impossible to keep this data in memory. Okay, now because this set of constraints, 7, plays kind of a separate role from this set of constraints, 8, which we call the convexity constraints, so 8 and 9, we associate dual variables pi I with the constraint 7. Okay, and dual variables mu k with each of these constraints. We've seen, if you go back to the start of this course, that for each LP we can set up a dual, and the dual has one dual variable for every primal constraint. So therefore I can go through this constraint by constraint, excluding these bound constraints, and each of these is associated with a dual variable. How many of these constraints do I have? Well, I have exactly the number of m, right? Whatever m is the size of this vector b. So therefore, pi takes that is of size m, and then for each of these constraints, of which I have k, because I've got k, capital K, many blocks of my decision vector, I've got an associated dual variable mu k. Okay, so we wish to apply the simplex algorithm to this LP master problem, but we find that this is impossible because there are simply too many columns in this LP. Right? The number of rows is not such a problem. It's the number of columns because we split each of these discrete sets xk into an enumeration of solutions, and then we introduced one variable for each of these. So we've got way too many variables. But here is where the fundamental trick of delayed column generation comes into play. We can say that most of these variables will be non-basic variables. There are only a few of these that will be basic variables, right? And so, strictly speaking, we do not need to know all the columns of our matrix A of all the non-basic variables, right? In particular, I could make an initial guess as to which variables I really need. If I had a smart way of guessing which of the lambdas are really required and are really non-zero, are required to become basic variables in the optimal solution to this LP, if magically you hand me this solution, right, or a set from which I know a subset of these will be the optimal basic variables, then I could forget about all the other columns, because it would mean that simply I set all the remaining lambdas to 0. All the lambdas that are non-basic variables are set to 0. And so therefore, my system of equations in constraint 7 will massively reduce. There's just a sub-matrix A tilde of my massive matrix with all these columns. I'm only retaining the columns that I really need. And I only retain the lambdas that I really need. So it's a convex combination of these columns that must be equal to the right-hand side B. I wrote B tilde, but it's the same as B. And correspondingly, because all the remaining lambdas would be fixed to 0, it's only the coefficients of lambda that are in lambda tilde that pick up, that contribute to my sum in the objective, because the remaining variables are equal to 0, so they don't contribute. So there's a subvector C tilde, right? So I write my C as a very long row vector, but most of the associated variables are equal to 0, so therefore I can forget about these components and push everything together, and I get a much shorter vector C tilde. And so I could then just solve this problem. This would be the restricted LP master problem. Of course, most of the time I will not get my guess as to which subset of indices contains all the optimal basic variables right. So I will have to have a mechanism by which I can change my opinion. Okay, but here, nonetheless, this is how we proceed. We make an initial guess, and we need to have at least one column. So we need to make a selection of a subset of columns of the big matrix A, right? At least one from each case, so that we can actually satisfy these constraints. And therefore, implicitly, we're setting all the remaining lambda kts equal to 0. The lambda kts that correspond to rows that we did not select, columns that we did not select. We fix those lambdas to 0. In that respect, it's a bit like a block coordinate descent method, right? A block coordinate descent, I don't know if Cora talked about this in her course, is looking at very large-scale continuous optimization problems, and then says, okay, well, we want to make progress. We want to minimize f, say. We're at the current point. So we choose a subset of variables, right, that we want to change, and we keep all the other variables fixed. So that reduces the dimensionality of the problem. And specifically, if the constraints and the objective support this in turning this into a simple enough structure to solve these subproblems more easily, then you can make progress and then update another block of variables and so on and so forth. And so here what we're essentially doing is we're saying we're fixing one block, a huge block of variables to 0, and we make progress on the other variables. Okay, so conceptually now we can solve this problem, and we will see an example, a numerical example at the end of this lecture. I think I have time to do that. Solve this restricted LP master problem. And then conceptually what we want to do now is, once we've done that, we want to use this optimal solution to identify a new and improved selection of a guess of indices, right, of variables that have amongst them the optimal set of basic variables. So we set up a new restricted master problem. We can solve this new problem using a worm starting simplex technique or any other worm starting LP methodology and carry on. So there's actually part of this mechanism that's still missing is, how do we use the optimal solution to one of these restricted LP master problems to identify the next restricted LP master problem? Let's call it RLPM plus. Okay, so this is how it is done. We solve our restricted LP master problem to optimality. Let's call the optimal objective value Z tilde LPM, right? We're not looking at all the feasible points of the original set because a large number of the lambdas were fixed to 0. So we're only looking at a subset of possible solutions. We optimize over these and we find the optimal objective value by solving this LP. If we use, for example, the simplex algorithm to solve this to optimality, then from the optimal tableau we can also read off what the associated optimal dual variables are. So this restricted master problem has a dual, and we can read off from the optimal tableau of this restricted master problem, we can read off what the optimal dual variables are. What's interesting about this is that we can take our argmax, the optimal solution to this problem, right? Let's call it lambda tilde star, and we can extend it to a feasible solution of the full LP master problem simply by setting the remaining lambda kt's equal to 0. Well, because after all, these are the variables that we fixed to 0. We forced them to be non-basic variables. So certainly what this yields by solving this is a lower bound on the optimal solution or optimal objective value of the LP master problem. Therefore, our optimal value, objective value on the restricted LP master problem, which we call Z tilde LPM, has a lower bound on the optimal value, objective value of the full LP master problem. But this happens to be C tilde transpose lambda tilde star, where lambda tilde star is the optimal, the argmax of our restricted master problem. And by strong LP duality, this happens to be equal to the dual objective value achieved by the optimal dual variables or values that we read off from the optimal tableau for the dual of the restricted LP master problem. Now, you look at this and you say, well, this therefore, we're not sure if pi mu is an optimal value or even a feasible value for the dual problem of the full LP master problem. If it were, then immediately this would show that lambda star extended by setting the remaining variables equal to 0 would be an optimal point for the LP master problem. Yeah? But so we need to now check. We need to check whether or not this pi mu is dual feasible. How do we check that? Well, we simply set up the dual of the full LP master problem, and it has these constraints here, namely that pi transpose ak x plus mu k must be greater or equal to ck transpose x for all x in all xk and k going from 1 up to k. So a large number of constraints. So how could we check that? Well, we see, and this is where the strength of this approach comes in. We're right at the heart of the strength. In order to check that, I can do this for over each subset xk separately. So I can write down an optimization problem over this set x, capital Xk, which is to maximize this left-hand side. And if this left-hand side, maximized, is smaller than 0, for all k, and I call this maximum zeta k, then the point pi mu is dual feasible for the LP master problem. If I look at this problem, I see that it's again an IP because xk, after all, is a discrete set defined as the intersection of a certain polyhedron with the integer lattice, like so. And so what have I gained? I mean, I started with this original IP, right, which has a structure that we depict over there. Then we expanded the number of variables by this implicit enumeration of all these sets xk, thereby ending up with a much, much larger IP. Then we looked at the LP relaxation of this, and now we generated a candidate for a dual solution for the LP master problem, which, to check whether or not it's dual feasible, requires us to solve these IPs. But see, these IPs are of much, much smaller size because they only operate on the block xk, which has nk decision variables, whereas the original IP had some of nk decision variables. Thereby, I can solve each of these problems in parallel, right? And these are much smaller problems. So at this point, I can really farm out these decoupled local problems, solve them, and bring back my solutions, the zeta k's, and check whether or not that is a feasible, dual feasible solution. If it's a dual feasible solution, then I know that lambda tilde star is the optimal or a optimal solution to my LP master problem. If not, then I can use it to make progress in that I set up a new LP master problem, restricted LP master problem. How would that happen? Well, let's look at this. So if zeta k is 0, if zeta k is smaller or equal to 0 for all k, then lambda tilde is optimal for the LPM, the LP master problem. Since pi mu is now dual feasible for feasible for the dual of the full LP master problem, and we know that LPM, ZLPM, the optimal objective value of the full LP master problem, is an upper bound on Z tilde LPM, the optimal objective value of the restricted LP master problem, which is C tilde lambda tilde, which is equal to this business. So that comes from the previous slide. But that must be greater or equal to ZLPM because this is now a valid upper bound on ZLPM because we've detected that pi mu is dual feasible on the full LP master problem. Therefore, this dual objective value must give us an upper bound. We said it's dual feasible. We're not sure if it's dual optimal, but it's dual feasible. Therefore, that must give us a valid upper bound on ZLPM. And we've got ZLPM on both sides. Apologies for the missing parentheses. So in this entire sandwich, all the inequalities are equalities, right? Which shows that lambda tilde must be optimal for the LP master problem and pi mu must be optimal for the dual of it. So in that point, we've solved the LP master problem. On the other hand, if we're not in this situation, right, if not all the zeta k's are smaller or equal to 0, then there exists at least one k for which zeta k is strictly positive. And in this case, we identified a column that we'd like to add to our matrix, right, our set of columns amongst which we want to choose our optimal basic feasible variables or basic variables. So now it seems that we keep adding more and more of these. So we can add that new column, and we have a larger set of columns, right? And we can set up our new restricted LP master problem, solve it again, and so on. And so we can see that potentially there's a problem there because as we keep adding more and more columns, at some point the matrix may become too large to keep in memory, and we might have memory issues. So the two things can be said about that. Every time a column enters, so the reason why we generated this column is because this is a variable that we'd like to make a basic variable. So if it enters as a basic variable, similar to a set of basic variables, then there will be a basic variable that leaves the basis as well and will become non-basic. This corresponds to a column that we've already generated, and it would be maybe nice to keep that column since we've already generated it, but we could discard it and regenerate it at a later stage. So this is one way of getting around this issue. But another issue that helps us is that if we can compute dual bounds, then since we've already got a primal bound, we've got a feasible solution to a restricted LP master problem, right? So that gives us a lower bound. If we also had a dual bound, then that would allow us to make progress with our branch and bound without having to solve our LP to optimality. Because after all, the reason why we want to solve these LP master problems is because we simply want a dual bound. So that going back to the LP-based branch and bound methodology, we keep tightening upper and lower bounds and making progress on the overall goal of solving the original IP that we formulated at the outset, the IP that has a special structure. So maybe we don't even have to solve the LP to optimality, the LP master problem to optimality, in order to get a good dual bound. So how would we calculate a dual bound? Well, this is where we can basically just recycle work that we've already done. So it doesn't require anything else. Because we computed the zeta k's as the maximum of this expression over x in xk, we know that for all x in xk, this quantity must be smaller or equal to 0. So that means that if you change your mu k by adding zeta k to mu k, you amend your dual solution that comes from the dual of the restricted master problem into a dual feasible solution of not the restricted but the full LP master problem. So using this amended dual solution and substituting this into the dual objective function, we end up with a feasible dual objective value, which of course is a dual bound. It's an upper bound on our LP master problem. We call that Z tilde upper bar LPM. And that's a valid upper bound. So that allows you to make progress in the branch and bound even without solving these LPs to optimality. And so the one thing we haven't discussed yet is how we would branch in this branch and bound methodology. And this specific way, there's a specific way of branching that comes out of this approach of delay column generation that we call branch and price. So that's the last element that we need in order to know how to do branch and bound on these very large, very structured IP instances. So again, we go back to the master problem, which is of this. And in fact, I just explain how you would branch at the top level of this decision tree. But as we will see, every subproblem that appears further down in the branch and bound decision tree will have the same structure, and therefore the same methodology can apply to it as well. So let's look at this master problem, okay? And as we saw, we then look at the LP relaxation of it, solve this LP relaxation using the delay column generation methodology in order to get a dual bound on this problem. This will be the first stage in solving this problem, this master IP via branch and bound. But now you see that in this representation we use the Danzig-Wolff reformulation, which is based on reformulating enumerating each of these sets xk, the constituent sets, by a large number of constituent points xkt, and each of these are binary vectors, right? And each of them are distinct binary vectors. And so therefore, if I'm writing xk tilde as this linear combination of xkt, in fact it's a convex combination in the LP relaxation of the master problem, then this ends up being an integer vector if and only if lambda tilde is an integer vector. And that's because these points are all different, right? They're all different, and so if any of the lambdas are fractional, then some of there's at least one variable, one coefficient of this of this vector x tilde k that will be fractional as well. So if the optimal solution of lambda tilde of the LP master problem is not integer, and that's a situation where we'd like to use fractional branching. So going back to what we did in LP-based branch and bound, we solved the LP relaxation, then we checked whether or not the associated solution happened to be integer feasible, in which case we'd have solved the problem to optimality. But if not, then we could use the fractional information about the optimal solution to split our set into two subsets. So in this case, this would happen because lambda tilde, the optimal solution to the LP master problem itself, is fractional, right? So if that's not integer, then there exists some fractional coefficient. So this vector x tilde k will have some component j that will be fractional, right? And so we'd like to branch by splitting the feasible set into two subsets, one where this component has to be rounded down, right, to the next possible integer, which is 0, and one where it's rounded up, which is 1. So in fact, what we're doing is variable fixing, because these are binary variables. So using the fractional branching, this then fixes what this coefficient would have to be. Yeah, the question is, can we identify what the master problems are that correspond to these problems where I introduce this variable fixing? Can we represent these problems in the same form so that we can use the same approach of column generation and the same time of branching further down in the branchings? Yes, this can be done. We have to identify this kappa, right, for which we're looking at this fractional branching, and then we either want to fix coefficient j of the corresponding vector to 0 or to 1. So we're looking at two subproblems, as delta for delta equal to 0 and 1. And in both cases, we need to treat the k's that are different from kappa separately and force all the lambda k's for which the jth, all the lambda kappa t's for which the jth component of the vector x kappa t is not equal to delta, delta being 0 or 1, depending on our choice, fix the corresponding lambda k's equal to 0 because they must not be strictly positive. And so essentially what this means is that we again end up with a problem that has the same structure as the master problem, but some of the lambda k's, so some of the lambda kt's or lambda kappa t's are fixed to 0. So this is good, right? Because we actually have fewer decision variables. This helps us. This makes the problem smaller. So both more restricted, but also smaller in terms of the number of decision variables we need to consider. So the only other slight change that we need to do is that when we check for the dual feasibility of the associated dual solution that comes out of the optimal tableau from the restricted master problem, we need to amend the problem to solve in the case of where k is equal to kappa, because we need to fix the corresponding the jth component of these decision vectors to delta, depending on what delta is, delta 0 or 1. And so essentially we're optimizing here, we're optimizing over a subset of the set xk. The subset being given by, again, the intersection of the integer lattice with a polyhedron that now has reduced dimension because we're fixing one of the variables. But conceptually, mathematically, this has the same structure. Okay, in the remaining few minutes, I want to show to you, and this is where it becomes less abstract again. So those of you who sort of disengaged in the last few minutes because the notation became a bit overwhelming can do a restart. You've got another chance of understanding this by looking at a very specific example, which is the cutting stock problem. The cutting stock problem is a classical problem that appears in many contexts, but sort of classically, as all these IP models are, explained in the context of cutting large paper rolls into paper rolls of smaller widths. So in paper factories, you make these paper rolls that are sort of a few meters wide, and then you get orders, right, for paper sizes of smaller sizes, and then what you want to do is you can set sort of knives, roll through. It cuts this up into shorter widths, and then you've got a cutoff at the end that you have to throw away. Well, you recycle it, but there's a cost associated with that. So here we assume that you have a factory that produces an unlimited stock of 20-inch paper rolls, and it can cut these into smaller widths. And they receive, here's a small scale problem. In reality, these rolls are much larger. They're sort of 4 or 5 meters wide. 301, an order of 301 9-inch paper rolls, 401 8-inch paper rolls, 201 7-inch paper rolls, and 501 6-inch paper rolls. So in this case, we've got 4 different sizes. And so we assume here that both trim loss, the cutoff at the end, that's a waste, and overproduction is also a waste. So in reality, usually you keep overproduction in the warehouse somewhere, but let's assume that is also waste. And so how can we fill all the orders under minimal cost? I mean, this business with throwing away overproduction basically means that you just want to fill the orders with the minimal number of paper rolls, because it's a fixed cost. The paper roll, the cutting itself, costs almost nothing. So in this case, we could now set up an IP that kind of takes this structure, but we kind of go straight to the dancing and wolf reformulation by saying what we will do is we collect all these different widths, right? And maybe we've got k different widths, m different widths, right? And then we're looking at all the possible patterns by which we can cut these longer rolls, right, these wider rolls of width w, in our case 20 inches, into patterns of shorter rolls of the required widths. Of course, we're not producing widths that haven't been ordered, in such a way that they fit into one of these rolls. Yeah, so for example, if I look at this 20-inch paper roll, I can see that I can cut a pattern of one 9-inch and one 7-inch roll. Right? But then I don't have any space for another 6-inch paper roll, but I could also, another pattern would be 3 6-inch paper rolls. Yeah? So conceptually, I can enumerate all these possible patterns, but of each pattern, if I look at pattern J, it would have aij repeats of width I, right? And of course, these must be integers, right? Non-negative integers. Could be 0, but non-negative. And then if I take that many times the width I, and I sum all these widths, that must be smaller than the total width, the 20-inch of the stock rolls. So all the aij's are non-negative integers. And now conceptually, I could generate all these patterns and assemble them into a large matrix A. Of course, in our case, it's quite restricted because we only have 4 different widths, but in reality, you've got many more different widths, and the W might be considerably larger than 20 inches, so you've got a huge number of possible patterns. And our decision variables here, which correspond actually to the lambdas in a way to before, so it's a bit confusing regarding the notation, but here I'm following the approach of Gilmore and Gomeroy. Our decision variables would be xj, which is the number of times we use pattern j. So each pattern can be used a number of times. And so if you now have our column vectors of patterns, right, and then I tell you how many times I'm using each pattern, then I'm adding, right, these columns multiplied by the jth column multiplied by xj, adding them all together. I would have to find that in the end I get exactly the number of rolls of each width that were ordered. Well, okay, you might say it must be greater or equal to, and then we have some waste, right, because of overproduction. But without loss of generality, I can make sure that this is exactly equal to B. Our objective is to minimize the total number of rolls used. So I'm minimizing the total number of rolls used. I use pattern j xj times, so the total number of rolls used will be the sum of the xj's, because each pattern uses one stock roll, subject to these constraints. The LP relaxation can be written up, right? That just relaxes these integrality constraints. And I can write down what the dual of this problem is. This being just a vector of all ones, right? And now what we do is we use delayed column generation to solve this LP because we have too many columns. And in this case, we just use m columns each time, then identify an entering column, so a new column is being generated. The leaving column we could keep in memory, but we don't. So we just throw it away and regenerate it if it's needed again later on, if this variable should re-enter. And so we can start with simple patterns, which is just I check for each width, how many times does it fit into a stock roll. So take the width of the stock roll divided by this width and then round it down. And so these are m patterns that I can start with that guarantee me that I will be able to fulfill all the orders because I'm producing some rolls of each width, right? So therefore I can actually do this. And I can easily say how many. In fact, x tilde will just be the optimal solution to this restricted master LP, will just be A tilde inverse B. Now, of course, this is a fractional vector. But I can also compute the associated dual variables. Y tilde is A tilde inverse transpose times the vector of all ones. And now I need to check whether or not Y is dual feasible. So that's my Y corresponds to the pi mu, right? Variables that I had before. I need to check if it's dual feasible. Well, if it's dual feasible, either it's dual feasible, then if it's dual feasible, then x tilde is optimal for the master LP. But if it's not, then there exists a pattern that can serve as an entering variables as a non-basic variable xj for which the corresponding column in my big matrix A hasn't been generated yet, but now I'm generating it. So I can so this can enter the set of basic variables. And so this is identified, if I can identify a J, right, such that the corresponding dual constraint is violated, right, then that is a good pattern to pick. But how can I check this when I haven't even generated these AIJs, right? For the J's for the columns that I haven't got in my set of columns that I generated. Well, I can do that by looking at the argmax maximizing y tilde trace p, y tilde transpose p, which is this. So basically, I'm looking for patterns, right? I'm say an unknown pattern. Let's call this pi, right? I'm trying to find a vector p, which must be integer, component-wise integer or non-negative, and I'd like to maximize this, but it must be a valid pattern. That is to say, I must be able to choose the coefficients of p as my entries of my column A. In other words, if I multiply the number of times I cut width I in this pattern, and I add up all these widths, must be smaller or equal to the width of a stock roll. So it must satisfy this constraint, have a single inequality constraint. And this type of problem is called a knapsack problem. You may have seen it before. These are some of the easiest, if you will, NP-complete optimization problems to solve. I mean, easiest as in there are some really good heuristics to solve these problems. Of course, the problem is NP-complete, so you can generate some really hard problems, but generally they're easy to solve. And in particular, branch and bound on these problems runs blazingly fast. It's really impressive. So we can solve this problem And this gets us to the point where we had our decomposition, in the general branch and price methodology, where we needed to solve these subproblems on these of much smaller and simpler kind. This is the specific problem that we end up with in the case of the cutting stock application. So having solved that, you can check if it's dual feasible, right? Dual feasibility of y would mean that the optimal value would be smaller than 1. If you choose p, this should be a p star here, then it's dual feasible. Therefore, your x tilde that you had was the optimal LP solution. Otherwise, you can use the optimal p star that comes out of this as the entering pattern. So you can make further progress by using this pattern. This is now the entering variable. And the exiting variable is determined in the usual way that I explained at the start when we discussed the simplex algorithm. So I have 3 minutes left, and we can make this even more concrete by looking at a specific example, namely going back to our example 8, where we had these 501 orders of yada, yada, yada. Okay? If I look at how many of these 9-inch rolls fit into a 20-inch roll, there are exactly 2, so I have a pattern of cutting 2 of these 9-inch rolls and 0, 0, 0 of the remaining is one possible pattern. I do the same thing with the 8-inch rolls and the whatever it was, 7 and 6. And so that's my initial choice of columns. I know A contains many, many, many more columns, but I don't need to initially generate them. This is a matter of to be dealt with as we go along and as we take pivoting steps. We generate each column only if and when needed. So here I'm proposing to solve the LP master problem. So our original solution, the solution to the restricted LP master problem, is simply the inverse of this matrix times the right-hand side vector B, which happened to be 301, 4, 1, 2, 1, 5, 1, the number of orders of each width. And it gives us these values for x. Of course, it's fractional, right? It's fractional. So therefore, this is certainly not an optimal solution to the IP master problem, but it's an optimal solution to the restricted LP master problem. The associated objective value is 618. So that's how many paper rolls I need, right, to fill this order. And now I compute the associated dual variables, which are given by 1/2, 1/2, 1/3. And then I check whether or not these happen to be dual feasible. So to do that, I need to solve this knapsack problem. You see, you recognize that 1/2, 1/2, 1/3 comes from this vector y, right? Now we're trying to find new patterns of 9-inch, 8-inch, 7-inch, and 6-inch paper rolls to be cut out of 20-inch paper rolls so as to maximize this objective. And we find that the maximum is 4/3, which happens to be strictly greater than 1, which gives us a proof that y was not optimal, was not dual optimal, was not dual feasible. Yet that doesn't mean that this is the end of the road, because at the same time, in this case, this identifies P star, the optimal pattern we find under this knapsack problem, which was solved using branch and bound on a knapsack, and this gives us this pattern as an entering column. Okay, so we'd like to use this pattern as one of the columns, but we need to find another column to kick out. I'm doing the usual computation of the upper bounds. So the associated variable, I want to move away from 0, make it positive. The further I make it positive, the more it's risking to make one of the existing basic variables negative. So each of the existing basic variables will give me an upper bound by how much I can move my new variable away from 0. The most restrictive is given by x3. So x3 is now a leaving variable. So anyway, what was it, x4? I don't know. But anyway, this is my new matrix, I compute the new associated vector, new associated objective value. See, this has come down. And then I keep going. Next time, I find another pattern that enters, and I can reduce the objective value even further. And this time, I find that the associated y is dual optimal, it's dual feasible. And out of the general theory comes immediately certificate of optimality both for x and for y for the LP master problem. Now we've solved the LP master problem. And so we see that 551.625 would be a lower bound in the number of paper rolls that we need. Of course, we need an integer number of paper rolls, so 552 would be a lower bound. And there is a way of using rounding. In this case, rather than doing branch and bound, there are sort of simple rounding procedures which don't always work, but often work, that in this case produces a solution that takes on this value 552, and that's the optimal number of paper rolls that we used in this case. So that brings me to the end of these lectures. If you have any questions, please don't hesitate to send me any emails. Otherwise, refer to slide 3 of this course, where I have loads more sources from where you can read up on these things. And it's, I think, an exciting approach to use in discrete optimization problems that appear in data science. Thank you very much.